The three-dimensional modes of packing can be easily understood by dividing the whole process into three steps. Close packing of spheres in one dimension. In one-dimension close packing, there is just one way of arranging the spheres. Here, the spheres are arranged in a row, touching one another. As a result, each sphere is in contact with two neighboring spheres. Thus, in one-dimensional close packing, the coordination number is 2. Close packing of spheres in two dimension. Close packing structures in two dimension can be generated by stacking rows of one-dimensionally closed packed spheres, one above the other. This can be done in two ways: square close packing and hexagonal close packing. Square close packing. In this type of packing, the second row of spheres is placed in contact with first row in such a way that the spheres of the second row are placed exactly above the spheres of first row. In such an arrangement, the spheres are aligned horizontally and vertically such that each sphere is in contact with four other spheres. So, the coordination number is 4. If we call the first row as A type row, the second row being exactly same as the first row, so it is also called as A type. If we keep on placing such similar rows one above the other, then such an arrangement is known as Aaa type of arrangement or square packing. Hexagonal close packing. In this type of packing of spheres, the second row of spheres is placed in a staggered manner such that the spheres fit in the depressions of the first row. If we call the first row as A type, then as the second row is different from the first row, it can be called as B type. Now, if we place a third row above the second row in the similar manner, we will observe that the third row spheres are aligned with those of first layer, and each sphere is in contact with 6 other spheres. So, the coordination number is 6. Similarly, on placing the fourth layer, we will observe that the fourth row of spheres are aligned with those of second layer. Hence, this type of arrangement is known as ABAB type of arrangement or hexagonal close packing. If we compare square close packing with hexagonal close packing, we will observe that empty spaces are less in hexagonal close packing than compared to square close packing. Now, what are these empty spaces and what role do they play in packing efficiency? The empty spaces in between the spheres are known as voids. These voids are responsible for decrease in packing efficiency of the solid crystal. More the number of voids, less is the packing efficiency of the crystal. Now, you must be wondering what is meant by packing efficiency. We have discussed about this in later part of the section. Now let us study about close packing in 3 dimension. 3-dimensional close packing from 2-dimensional square close packed layers. This type of packing is obtained by placing 2-dimensional square closed packed layer above the first one, such that the spheres of the second layer are exactly above the spheres of the first layer. In this arrangement, the spheres of both the layers are perfectly aligned horizontally and vertically. On arranging layers one after the other in this pattern, we will observe that each sphere is in contact with 6 other spheres. 4 from the same layer, 1 from the layer above, and 1 from the layer below that sphere. So, the coordination number is 6. If we call the first layer as A type, and since all the layers are also of the same type, this kind of arrangement is known as Aaa type of arrangement. On observing carefully, we will find that this arrangement has generated a simple cubic lattice, and its unit cell is primitive cubic unit cell. Dimensional close packing from two-dimensional hexagonal closed pack layers. The three-dimensional hexagonal closed pack structure can be obtained by placing two-dimensional hexagonal structures one layer above the other. Placing second layer over the first layer. Let us take a two-dimensional hexagonal closed packed layer A. Notice this layer has triangular voids. Place a similar closed packed layer in such a way that the spheres of the second layer are placed in depressions of the first layer. As the spheres of the second layer are aligned differently as compared to the first layer, so let us call this layer as B type. On observing, we will notice that not all the triangular voids of the first layer are covered by the spheres of the second layer. This gives rise to a different arrangement and different voids. Voids. There are two types of voids. Tetrahedral voids, denoted by T, octahedral voids, denoted by O. Let us study how these voids are formed. When we place a closed packed layer above the depressions of the first layer, we will notice that at some places the triangular voids of the first layer are being covered by the spheres of second layer. At such places, a type of void is formed. This type of void is known as Tetrahedral Void, T, since a tetrahedron is formed by joining the centers of the 4 surrounding spheres. While at other places, we will notice that the triangular voids of the first layer coincides with the triangular voids of the second layer, such that their triangular shapes do not overlap. At such places, another type of void is formed. This type of void is known as Octahedral Void, O, since an octahedron is formed by joining the centers of the 6 surrounding spheres. Now, in case we need to calculate the number of tetrahedral and octahedral voids in a crystal structure, then just knowing the number of spheres will serve the purpose. Suppose there are n spheres in the crystal structure, then the number of octahedral voids generated is equal to n. The number of tetrahedral voids generated is equal to 2n. Placing third layer over second layer. Now let us place third layer over second layer. Stacking of third layer over second layer can be done in 2 ways. First, by covering tetrahedral voids. Second, by covering octahedral voids. By covering tetrahedral voids. The tetrahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer will get exactly aligned with the spheres of the first layer. So, if we can call the first layer as A type and the second layer as B type, then the third layer will also be A type. As the pattern of spheres is repeated alternately in other layers, so this pattern is known as AB-AB pattern, and the structure formed is known as Hexagonal Close Packed HCP structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So the coordination number is 12. Covering octahedral voids. The octahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer are not aligned with the spheres of either first layer or second layer. So, if we call the first layer as A type and the second layer as B type, then this third layer will be C type. Now, if we place the fourth layer over the octahedral voids of the third layer, then the sphere gets aligned with the spheres of the first layer. Thus, this pattern is known as ABC type, and the structure formed is known as cubic close packed CCP or face centered cubic FCC structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So, the coordination number is 12.
हेलो, वेलकम टू केमिस्ट्री अनटोल्ड। सो बात करते हैं हेक्सागोनल क्लोज पैक स्ट्रक्चर की। डिटेल में पढ़ें।
Module. You will learn about the number of atoms in a unit cell. You already know that every crystal lattice is made of an infinite number of unit cells, and every lattice site is occupied by a constituent particle that may be an atom, an ion, or a molecule. Now let's examine what portion of each particle belongs to a particular unit cell. Consider 3 types of cubic unit cells. For the sake of simplicity, assume that the constituent particle is an atom. Let's start with a simple or primitive cubic lattice. A simple cubic lattice consists of 8 atoms at the 8 corners of a cube. In the open structure shown here, the distances between the atoms are greatly exaggerated. In reality, the atoms are packed much more closely together, as shown in the space-filling model here. The space-filling model shows that the atoms touch along the edges of the cell. By considering the portion of atoms inside the cell boundary, we can generate a unit cell of a simple cubic lattice. From this, It is evident that each atom at the corners contributes 1/8 of its original volume to each unit cell. There are 8 atoms at the 8 corners. Thus, the number of atoms in each unit cell is equal to 8 corner atoms into 1/8 of an atom per unit cell, which is equal to 1. A body-centered unit cell contains 8 corner atoms, just like in a simple cubic unit cell. However, there is one more atom at its body center. As a result, the atoms at the corners no longer touch along the edges of the cell in the space-filling model. The unit cell of a body-centered cubic cell is shown here. It is clear that the 8 atoms at the corners contribute 1/8 of their actual volume each. In addition, one atom lies completely inside the cell. Therefore, the number of atoms at the corners per unit cell is equal to 8 corner atoms into 1/8 of an atom per unit cell, which is equal to 1. There is one atom at the center of the cube. Thus, the total number of atoms in a body-centered cubic unit cell is 2. The face-centered cubic lattice consists of 8 corner atoms, just like in the simple and body-centered cubic lattice. However, it also contains 6 more atoms at the 6 faces of the cube cell. The atoms touch along the diagonals, and each touches 4 corner atoms. A unit cell of a face-centered cubic cell is shown here. It is clear that the atoms at the corners contribute 1/8 of their original volume each. In addition, there are 6 atoms at the 6 faces, which contribute half of their original volume each. The number of atoms at the corners per unit cell is equal to 8 corner atoms into 1/8 of an atom per unit cell, which is equal to 1. The number of atoms present at the faces per unit cell is equal to 6 atoms at the faces into half an atom per unit cell, which is equal to 3. Thus, the total number of atoms per face-centered cubic unit cell is 4. You have now reached the end of this module. In this module, you learned that every crystal lattice is made of an infinite number of unit cells, and every lattice site is occupied by a constituent particle. There is one atom in a simple cubic unit cell. There are 2 atoms in a body-centered unit cell. There are 4 atoms in a face-centered unit cell.